We continue with section 2.4, example 3, part B. The next function whose domain we want to find is g of x equals the square root of 2x plus 1. Here the issue is avoiding negative numbers under the square root. Negative numbers under a square root are not real numbers. They are so-called imaginary numbers. So to avoid imaginary numbers, we want to take 2x plus 1, the expression under the square root, and ensure that it is always greater than or equal to 0. So we want to determine the values of x such that 2x plus 1 is never negative. Solving this inequality for x, subtract 1 from both sides to obtain 2x greater than or equal to negative 1. Then divide both sides by 2 to obtain x greater than or equal to negative 1/2. So what this is telling us is that so long as x is greater than or equal to negative 1/2, we will stay away from negative numbers under the square root. So the domain would be the set of all real numbers x such that x is greater than or equal to negative 1/2. In interval notation, that would be represented as bracket negative 1/2 comma infinity. The bracket is used with the negative 1/2 to indicate that negative 1/2 is included in the interval. Then the interval extends to the right indefinitely, so we use positive infinity, and with positive infinity we always use a parenthesis. Our next example, part C, h of x equals 2x plus 1. Here, there are really no restrictions on what we use for x. We don't have to worry about division by 0 because there are no fractions, and we don't have any square roots. So really, we can substitute anything we want for x, and we'll get a real number as our output. So our domain could be described as the set of all real numbers x such that x is any real number. Sometimes that's expressed this way: x is an element of the real numbers. The r represents the set of all real numbers. In interval notation, this is represented as minus infinity to infinity. So the set of all real numbers. So the domain is the set of all real numbers. So this function has an unrestricted domain. And then for our final example, for final function for example 3, capital T of t equals 1 over t squared plus t. Here the issue is the possibility of division by 0. How do we determine the values of t such that the denominator is 0? Well, take the expression in the denominator, set it equal to 0, solve the equation. Notice we can factor a t out. T times t plus 1 equals 0. Then set each factor equal to 0. T equals 0, or t plus 1 equals 0. The second equation is solved as t equals negative 1. So both 0 and negative 1, if substituted into this function, will give us division by 0, and hence will not give us a real number as an output. So the domain for our function capital T would be the set of all real numbers little t such that t is not equal to -1 or to 0. So in other words, we have to leave -1 and 0 out, but we can use anything else. In interval notation, that's represented as follows. We're going to go from -infinity to -1, but leave -1 out. Then we'll go from -1 to 0, again leaving both of them out. We're using parentheses, as you can see. And then we can go from 0 to infinity. And we connect these with union symbols. So essentially it's all of the real numbers on the real number line, but leaving two of them out, -1 and 0. And in interval notation, that requires you to write 3 intervals connected with union symbols. So it can be a little bit tricky with the interval notation. Takes some practice, but this is how it has to be done to use the notation correctly. And you will be expected to do it this way when you enter your answers in MyMathLab. We continue to the next page now and continue our discussion of domain. Note that the domain of a function may be restricted either explicitly or implicitly. You might say directly or indirectly. For example, if a function is stated as f of x equals 2x plus 1, where x is greater than or equal to 0, then we see the domain is explicitly or directly restricted to the non-negative real numbers, to the numbers greater than or equal to 0, because it's part of the way the function is defined. We're told x has to be greater than or equal to 0. We don't know why in this case, but that's the part of the definition. That is, the domain is the set of all real numbers x such that x is greater than or equal to 0. That is, bracket 0 to positive infinity. For the function c of r equals 2 pi r, where r is the radius of a circle and c is its circumference, the domain is implicitly, indirectly understood to be restricted to the positive real numbers, even though it's not stated as such, because we're talking about some physical object, a circle, and the radius of a circle must be a positive number. It doesn't make sense to have a radius of 0 or a radius that's negative if you're talking about a circle. So implicitly it's understood that the domain has to be the set of all real numbers r such that r is greater than 0, or parentheses 0 to infinity. That is, positive real numbers only, because we're talking about a radius. Now our next topic is the graph of a function. To understand functions well, it's very, very helpful to be able to view the graph, and that's something we will touch on repeatedly in this course. The graph of a function f is the set of all points x comma y such that x is in the domain of f and y is equal to f of x. In other words, the graph is a set of all points x comma f of x. Remember that the f of x's are y values. So when you compute an f of x value, you're computing the y coordinate of a point on the graph of the function. Not every graph is that of a function. Some graphs are merely graphs of relations between x and y that are not functions. There is a test that we can use to determine whether a graph is that of a function or not, and that's called the vertical line test. It's very easy to apply. If no vertical line intersects a graph more than once, then the graph is that of a function. The vertical line test is essentially the graphical way of restating the definition of function. In other words, for every x, there must be, for every x in the domain of the function, there must be one and only one y value associated with it. That means any vertical line must intersect the graph no more than once. I'll explain that further in a moment. Example 4 says, determine which graphs are those of functions. Our first example is not a function, because if we just look, say, at the y-axis, which is a vertical line, it intersects the graph at 3 different points, meaning that for x equal to 0, there are 3 different y values associated with that one x value. And that does not satisfy the definition of a function. For a function, every x can only be associated to one and only one y. Here we see a specific x equal to 0, that corresponds to 3 different y values. So the answer here is no. This is not the graph of a function. This graph does not pass the vertical line test. The other 2 graphs, however, do pass the vertical line test. Any vertical line that we draw through the graph should intersect the graph at one and only one point, meaning that for those values of x, there's one and only one y value associated with each of them. Now the graphs may get rather steep, but they never go vertical themselves. This is something we commonly see. We often see that the graphs get quite steep, but they never attain verticality, and in those cases the graphs still do satisfy or pass the vertical line test. So the answer for the second and third graphs is a yes. Those are indeed graphs of functions. Another thing we can determine from the graph of a function is the domain and the range of a function. In particular, the range is much more easily determined if we can look at the graph of a function. Otherwise, the range can be quite difficult to determine. The domain we can often determine directly from the equation or formula that defines the function, but the range can be quite difficult to determine if we don't have a graph. Given the graph of a function y equals f of x, the domain of f can be thought of as a set of all x coordinates of points on the graph, and the range can be thought of as a set of all y coordinates. So when we look at the points on the graph, the x's, the x coordinates, belong to the domain of the function, the y coordinates belong to the range. So if we project the graph onto the x-axis, as is shown in the sketch, you see that the x values range between x equals a and x equals c and everything in between. So the domain for this function that's shown could be expressed as bracket a comma c, the set of all real numbers between a and c. The range, the set of all y coordinates, is the projection of the graph along the y-axis, and you can see that that ranges from y equals b to y equals d and everything in between. So if we project the graph along the x-axis, we get the domain. We can determine the domain of the function. If we project along the y-axis, we can determine the range of the function.